Faith, welcome. Hey, Kim. Good morning. Welcome back. A busy class today. One last busy class. I'll slow down after today. Good morning. Hello, Alex. Good morning. Hello, Wendy. Welcome back. Hi, Jumila. Welcome back. Hi, Nadal. Welcome. All right, welcome back. Hopefully you guys had a good day off. Hopefully you guys are rested, all up to date with your notes, and ready to roll for chemistry class. A little heads up, today's class is going to go pretty quick. There's going to be a lot of stuff I'm going to be throwing at you guys for this class. Just want to make sure we're all good to go for the benchmark exam, which will be next class. So brace yourself, get yourself comfortable, get yourself in a nice learning environment, put some headphones on because today's a big class. It's going to feel very rushy. Again, I'm going to record it in the event that you need to rewatch it and you fall behind. You have the ability to rewatch it, or you can just view a certain portion of the video that you need or maybe missed. So here we go. Please check the intents to the left. Please make sure it's accurate, precise. I'm just missing Frank and just missing Philip, but they may pop on in here. So we'll see. All right, before I jump into today's class, I do want to check out this chart right here. Hi, Philip. Welcome. Try to get here a minute or two earlier, please. Okay, I do want to analyze this chart here. Great. Don't do this to me. Oh, my toolbar for Zoom's stuck at the top. This is not going to be good, but we'll get through it. Can't move my Zoom bar. Hi, Frank. Hi, Emma. All right, so anyways, I do want to analyze this chart for coronavirus. It's happening pretty popular now, going on. Stinks is coming back, it's making a run back. But anyways, this is like March 13th, Friday, March 13th, before school ended last year. And then what happened, we had a couple cases starting to pop through. Then you could see it started to increase pretty quickly in May, up to 32 cases, roughly. It's a daily positive. But anyways, the other chart was the average of 3 days. So May 4th, the highest number is 63 cases per day in Oneida County. Oneida County is a big county, but just analyzing this. So in Oneida County, the highest was 63 cases. And then after that point, it started to descend from that point. It descended. That was the first wave. So you could see the first wave increased. And then it started to flatten out beginning of the school year. But it wasn't gone at this point. It was still there. And now we're starting to see a second wave come on through, which is pretty scary in my opinion. Because last few days we had 24 cases, 32, 49, 48, 43, 36, and then yesterday we're at 74 cases. So the number of cases is increasing pretty quickly at a quick rate. So that was just the number of people that were diagnosed in that one day. There's more than that have coronavirus in the area. So yeah, people are saying coronavirus, if you get it, not a big deal, but there are still casualties with the coronavirus. So I don't like the way this looks because this curve, you have a lot going on with this. You have obviously increase, decrease. This one's not even, maybe it's not done increasing. Hopefully it's done increasing. What goes up must come down. This went up in this time span. Took maybe 2 months to get that time span to the high. Look how long it took to get down. So maybe a antibiotic will come through. But the problem with the antibiotic is it going to be legit? Do you want to try the antibiotic that we don't know anything about? So be safe. Take caution. Wash your hands. Wash your face. Practice good habits for staying safe and clean. Social distance, wear a mask out in public, all that good stuff. All right. Let's move on forward here. Hide the controls. Our agenda for today, here we go. So welcome on back. Hopefully you had a good day off. We're going through the quote of the week, which is by Charles Schwindel. Life is 10% what happens to me and 90% of how I react to it. Whatever happens to coronavirus, stay positive. Daily agenda for Thursday, November 12th, 2020. It's a day 1. Unit 3, we're going to finish up the atom. It's going to be on ground state and excited state configuration. I'll start off with a YouTube video. We'll get through some notes, analyze some examples, another video again at the end. This YouTube video is 2 asterisks by it. This you're going to watch in your own time. Hopefully you can watch that maybe after class or when you have free time tonight. And then you have an exit pass that I would try to attempt today, so you can do them for the benchmark for tomorrow. You're going through, so this will take like 30, 40 minutes to get through this portion. The last 40 minutes of class, we're going to go through unit number 4. It's going to be like a really small snapshot of the periodic table. And a lot of the stuff you're already going to know. So organization of the periodic table, will go through a crash course notes on it. This video will maybe play if I have time, and then we'll get through some notes there as well. So that video, the second crash course video, periodic table, please watch that for homework on your own time. So here's a crash course video on the periodic table. The second one was on electrons. Hopefully you watched that one already. That's actually lower on the stream page, so please check that out as well. All right, let's go through some stuff today. Start off with a video, crash course video on what are electrons and excitation.
Electrons move around a nucleus of an atom in concentric orbits. These orbits or shells represent different energy states that electrons can exhibit. The farther an electron is from the nucleus, the greater its potential energy. While electrons typically remain in their prescribed orbital energy level, it's possible for an electron to be knocked from its lower orbit into a higher one. Thus, a bombarding free electron can collide with a bound electron, raising it to a higher orbit or energy level. This electron is now in a state of excitation. However, this higher orbital status is fleeting. The electron will be quickly drawn back toward the nucleus and return to its original orbit. During this transition back to its normal state, a single photon of visible light is emitted. This repeating sequence of electron excitation followed by de-excitation is the basis for the functional capacity of a fluorescent light bulb. A typical fluorescent bulb is filled with argon gas and a minuscule amount of vaporized mercury. The inner surface of the tube is coated with the powdery phosphor substance. At each end of the tube is an electrode with filaments. When heated to a high temperature, they emit or boil off electrons. An AC voltage pulse supplied by a starter pushes the electrons from one end of the tube to the other. If one of the free electrons collides with an electron of the mercury vapor, the electron is bumped from a lower to a higher energy level. The electron quickly returns to its lower energy state and in the process releases an ultraviolet photon. This photon is then absorbed by the electrons of the phosphor powder lining the tube, again exciting electrons in the process. This excitation is followed in turn by de-excitation and the release of a low-frequency photon. The photons from all these reactions combine to produce the glow of white light, characteristic of fluorescent bulbs.
All right, so that is exciting electrons. The last demonstration I did in class the other day, you saw the example of exciting electrons as well. The bell ringer for Na+, no, we don't have to worry about doing that one. I'm not going to assign that for Na+. So that one I actually will delete at the end of class today. All right, so moving on forward. So please open for guided notes, and we'll continue on the exciting electrons. You probably want a reference table for today as well. In the event I do go too quick, you're more than welcome to rewatch this video. All right, so the guided notes, here we go. We left off on this page. Let's go through a little snapshot of where we've been, where we're going through class today. So this is the last day for the unit for this note, so this packet of notes. So hopefully you have most of it completed. This will be due and turned in by Saturday. So that is the due date for the note packet. Hopefully you stay on task. We went through the history of the atom. We talked about Dalton Thomson with the cathode ray tube experiment. He discovered the electrons. We talked about Rutherford, the gold foil experiment, how they bombarded the nucleus and some particles bounced off. He discovered the nucleus. The atom is mostly empty space as well. Bohr, he discovered electrons orbit around the nucleus in shells. We did that. This topic right here is exciting electrons. Absorbing or gaining a certain amount of energy causes the electron to jump to a higher energy level. That video showed like an electron jumping right up. In the excited state, when excited states emit or lose energy, when they fall back down, they give off the light, the lower energy level. We talked about the wave mechanical model for orbital being the probability of finding electrons. We did S, P, D, and F. That's what the atom looks like today. We talked about an elemental box. Masses upstairs, the atomic number, proton number, the big bold number, electron configuration, we should know that one inside and out. And then the symbols there too. Oxidation numbers, we're starting to get into that with ions. We should know the proton has a mass of +1, and the charge is going to be +1. It is inside the nucleus. You should know the neutron is neutral, has a mass of 1 AMU, and that is inside the nucleus as well. The protons and neutrons are called nucleons, which are found inside the nucleus. Electrons are so small, so light, they orbit around the nucleus. You should know proton is the same thing as the atomic number and nuclear charge. You should know electrons are the same as protons in an atom, but ions, they could be different. Neutrons come from the mass minus the proton number. The mass number comes from the two things that have mass, the two subatomic particles that have mass, such as the protons and the neutrons. There's a boring for carbon. You should know atoms, the proton number and the electron number is equal. That's why there's no charge up here. It's equal to 0. You should know an ion is negative charge. Why is it negative? Because it gained an electron. It has more electrons than protons. Cation's positive. Why is it positively charged? Because it lost electrons. Hopefully you know that concept. You should know an isotope is the same element, but a different mass. Or the same element, different number of neutrons. You should know how to calculate atomic mass. The weighted average, the mass comes from the weighted average of all the naturally occurring isotopes. You should be aware of how to do that and calculate that. You should know electron configuration. If it's on the reference table, it's a ground state. You should know that the kernel is going to be everything besides the valence electrons. So kernel is going to be the protons and neutrons and all the non-valence electrons. We should know the valence electrons are the electrons in the outermost shell. We made some Bohr rings. Took us forever to make those Bohr rings. We made some Lewis dot diagrams for an atom, which was equal to 0 charge. We made some Lewis dot diagrams for an ion, which is a negative or positive charge. Negative charge, you need element name, the symbol, the brackets, the charge, and then you need electrons around it for negative charge, all 8s. Positive charge, you need brackets, symbol, charge, no electrons around it. We analyzed several of them. And we left off with the ground state versus excited state. So I did my little demonstration. There it is. And then we analyzed ground state versus excited state. So the ground state is how it appears on the reference table. It's the lowest possible configuration. The excited state is going to be when an electron jumps to a higher energy level. So here we go. The ground state configuration, electrons in the lowest energy configuration, found in the periodic table. Excited, it's found in a higher configuration. So this is where we left off yesterday in class. Let's get rid of that COVID completely. All right, so you definitely want a reference table as we go through today's class as well. So trying to figure out if something's a ground state or excited state, what do you do first? You add up all of those values. So please add up all those values. You'll figure out the atomic number. You can use your cell phone. You can use simple math. You use a calculator. I don't care. So 2 plus 8 plus 18 plus 8. Add it all together. Oops. Get rid of that one. Gotta do it again, I guess. Can't do it simple. 2 plus 8 is 10. Plus 18 plus 8, 36. So we got 36 when you add up all the electrons. Going to my reference table. I'm not an Islanders fan. Just whoever put that on there, put the icon for that. So now you're going to look for element 36 by matching up the atomic number. Find element 36. There it is. Find element 36. It's K, R, krypton. And the next thing you're going to do is going to take that number that we have, 2, 8, 18, 8, and match it up to the electron configuration on the reference table. If they're exactly the same numbers, then it's going to be the ground state. So those are exactly the same numbers. So this would be ground state configuration. If they're different, then it would be excited. Next one up.
What do you mean by different?
Like if it's at 2, 6, 18, 1 or something, then it'd be excited. So these match exactly up. They're exactly the same. The next one's gonna be different. So we'll see that. So please throw in the chat how many electrons do we have there? 2, 6, 18, 1. Please throw in the chat. Chat. Okay, so 27 electrons, thank you. What element are we dealing with? 27 electrons. Which element is that? CO. So find element number 27. CO. Element 27 is CO. Excited or ground state? Thank you. So match them on up. It's element CO. Match them on up. They're not the same, therefore, yeah, it's going to be excited configuration. Excited configuration. Last one. Please add those all up. 2, 5, 18, 32. Please throw in the chat. We'll do a lot of the chat work today. I'll wait for like 3 or 4 of the right answers. Yep, 57. If you add them all together, it is 57. What element are we analyzing now? Cool. So match it on up, find element 57. That's the atomic number. La, it's the lanthanides. Now we're going to match them on up. So it's element La, ground or excited. So you can see that they do not match up. So the two things I bolded, the left screen to the right screen, they don't match up. Since they don't match up, this is going to be the excited state configuration. So that is ground state and excited state configuration. The greater the distance from the nucleus, the greater the energy of the electron. So the further it jumps away from the nucleus, so if this guy jumped from the second ring to the third ring, it's a big jump there. Since it jumped further away, it's gonna have more energy, but you don't really know that one right now. Below that, I do want to talk about the maximum number of electrons in each ring. So the maximum number of electrons, so we're gonna fill this in too. Maximum number of electrons are going to be 2 in the first ring. The second ring has a maximum of 8. The third ring could have a maximum number of electrons of 18. And the last one could have a maximum number of electrons of 32. So 2, 8, 18, 32. It's going to tell you the maximum number of electrons that each ring could occupy, could have. But I think you guys could probably figure that out by just looking at the reference table. Let's look at a couple elements here. All right, let's just check out TC. TC, the first shell has a maximum of 2 electrons. The second shell has a maximum of 8, and all these, the maximum is going to be 8. The third ring has a maximum of 18, but if you scroll on the bottom, it has a maximum of 32 on the third ring. Remember that asterisk meant there's 2-8 in front of it. So 2 in the first ring, 8 in the second, 18 in the third, and the fourth one has a maximum of 32 electrons. That you should also be aware of. The maximum number of electrons per ring is 2, 8, 18, 32. All right, moving on forward for more exciting electrons here. So I'm down the reference table for now. When the ground state electrons are absorbing energy, when ground state electrons absorb energy, when ground state electrons absorb energy. It's like yesterday, think about it. I put some salts on the watch glasses. They weren't absorbing energy yet, but then when I lit them, what happened? They jumped up to a higher energy level. We'll give you an example in a second. Higher energy level or excited state. So how do you excite electrons? You add heat. If you guys get excited, because it's chemistry class, you're excited for chemistry class, you walk in the door, you're ready for chemistry class, the time's up for chem, you're excited. If there's another example, if there's a fire underneath your tail, you're going to jump up and say, oh, that's hot. You're going to get excited for a little bit, you're going to get away from the fire, and then you'll calm back down again. Just like my example yesterday, I put the alcohol on, I put the salts on, I lit them, it was lit, and then they were excited. They went to higher energy level. They're excited. This is very unstable or temporary, so it's not going to last very long for the excited state. So unstable or temporary condition. So my flame test yesterday in class, heat's electricity, stuff like that's going to make it something excited. So heat's definitely a huge factor. So they're unstable for temporary time. Once they're excited, so excited electrons rapidly fall back down. Fall back down or drop. Yes. Anybody have something to say? Joey, you have anything?
Oh, no.
No. It's all right. Hey. So they drop back down to a lower energy level. Lower energy level. So my flame test, they weren't going to stay those colors for an hour. They fell back down once the flame was out. Chemistry class, you walk into chem class, you're excited, but then when the bell rings, you de-excite. You guys cool back down. You're like, oh, I got to go to the next class. I understand. It happens. Every year I see it. I go through it myself, guys. I really do. Electrons, they rapidly fall back down to a lower energy level. When excited electrons fall from an excited state to a lower energy level, they release energy in the form of light. So this happens for fireworks. 4th of July, you watch the fireworks, give off the different colors there. The fireworks show lasts a long time, costs a lot of money, but it lasts a long time, but then it runs out. Each firework gives off its different or unique color, but then it stops. It goes, explodes, that's it, comes back down, then it cools on down again. So it gives off energy in the form of light. When it goes from the ground to the excited state, energy is absorbed. If you're absorbing something, you're taking it on in. Think about that process. ground to excited state. So if you just have an atom just hanging out, let me draw a picture over here actually. So there's an atom just hanging out, nucleus, 2 shells, we'll call this lithium. So you have nucleus and 2-1's lithium as a ground state. If it's just hanging out, if no heat's added, it's going to be in the ground state. If you add some heat in the situation, so I throw a little Bunsen burner underneath this or some sort of flame. Once I throw a little fire underneath it, it's going to start to get excited. These electrons. So what's going to happen if as I add heat, they're going to move quicker, quicker, quicker. Just like kinetic energy. As you add more heat to a heating curve, from solid, liquid, gas, as heat increases, these particles move quicker, quicker, quicker. You add more heat, this electron is going to jump on up to a higher energy level. So it goes from 2-1, that's ground state, and that's going to jump up to a higher energy level. So that one electron is going to work its way up to that shell. Let's get rid of that. Oops. So I went from the first shell, and it's going to jump up to the second shell. So when it jumps up to the second shell, now that's going to be the excited state configuration. So it's going from 2-1 to now 1 electron in the first shell, 1-2. So that's excited. But the thing is, that can't stay excited for a long time. So let's put this fire out. Put the fire out, throw some water on it. Fire's out. What's going to happen, that electron is going to fall back down to the original or ground state. So it's going to fall back down to here to be 2-1 again. Once it falls back down to 2-1, put another electron here again. There's 2-1 again. Once it falls back down, it gives off energy in the form of light. So different light would be given off as it falls back down. So that's ground state to excited state and excited state to ground state. In the process, what happens? You absorb energy, then you have to release the energy. All right, moving on forward. Absorbing of the energy, this causes a dark line spectrum. Dark line spectrum is produced when you go from ground to excited. If you go from the excited state to the ground state, energy is released or emitted. And this creates a bright line spectrum. When we get back to school, we'll do a lab on using bright line spectrums. We'll excite electrons, we'll excite atoms, and then we will look through a spectroscope. Spectroscope is going to break off the bands of light to distinctive characteristics. And then you see patterns like this for each element. So we're probably not going to be tested at all on dark line spectrum. I don't see any questions like that. I typically see questions on, excited to ground. Sorry, I got too excited. Excited to ground state, this typo there. Excited to ground, energy is released, bright line spectrum is produced. So this bottom one is a bright line spectrum. You could see that there's bands of bright light emitted in between all that blacked out. The one above, there's blackouts or dark lines in between this spectrum. So spectrum, you have Roy, G, BIV, red, orange, yellow, green, blue, indigo, violet. So these bands are going to tell you which element you're dealing with. I'm going to double click the text box to the right. This first one's going to be a dark line spectrum. Dark line. Dark lines show the specific wavelength of light energy being absorbed by the electrons becoming excited. The second one's going to be so once you're done, you can save it and close it. All right, I gotta refresh. It's probably gonna have to redo it because it wouldn't let me save it and close it. If you can't save it and close it, you just gotta refresh your screen. Probably gonna have to rewrite it in there again. Okay, so again, dark lines, it is there. Dark lines show a specific wavelength of light being absorbed. Now I can save it and close it, hopefully. It's odd. All right. And the one below is going to be the bright line spectrum. So the bright lines and they show specific wavelengths of light being emitted or released. Emitted or released. Save it, close it. So those are bright line spectrums. Okay, next up says the Balmer series, electrons falling from an excited state down to the second energy level. From an excited state down to the second energy level. And they give off visible light, also known as bright line spectrum, or the visible light spectrum. Different elements produce different colors of light or spectra. So every element, as you excite them, gives off a different spectra. And I'll show you an image in a second about it. These spectra are unique for each element. So they're all different for identifying which element you're dealing with. Each element produces different colors of light or spectra, bright light spectra. That wasn't the bell. Some laundry. These spectra are unique for each element, just like human fingerprints is unique for each person. We use spectral lines to identify different elements. So as you're still writing that out, I do want to analyze something here. This is the coronavirus curve for Oneida County, but this is the bright line spectra for every element on the periodic table. I'll go back to this in a second. So anyways, every element in the periodic table has a distinctive band of light that can be given off, emitted when you excite the electron. So if you were to excite a certain element, they give off a certain pattern of light. So I know this is blown up here and you can't really see the colors too well, but you could definitely look at H and say, oh, H has a red band, maybe a green, and maybe 2 blue or 2 purple bands. So there's 2, maybe 4 bands there. But if you looked at helium to the right, there it is. Helium has a different pattern of bands. Maybe there's 3 blue or purple, a green, an orange, and maybe 2 or 3 red. Those are definitely different. Let's just check out the one below. Neon looks quite a bit different than that. If you match them on up, there's different bands present for neon. There'll be different bands for each and every element below. So every element has a different pattern of bands. If you excite them, look through a spectroscope, it would give off the specific bands present for that element. So that's another way you can use to identify which element's present in the mixture. Pretty cool. And once we get back to school, we'll do a lab on this, one of my favorite ones. So we'll give you samples, so figure out the spectrums, the bright line spectra for each element as you excite them. All right, moving on forward. Please put the answers in the chat. Which of the following is a ground state electron configuration? Which one's a ground state electron configuration? Please put in the chat. I'll wait for 4 or 5 right answers and we'll move on forward. Yes, Nidal, thank you. Alan, yes. So a ground state configuration must occupy the lowest energy level first, then it can occupy the the next one. So 2 for the first one, has to be 8 for the second one, and 18 for the next one. So analyzing it, you can add them all together, figure out which element you're dealing with, 2, 7, 2, 9, 10, 11. So element number 11, you went through the first one, sodium. 281 is a ground state. 272 would be the excited state. 272 would be the excited state configuration. So the best answer for that one should be D. Hope that's good, Bellman. All right, so the best one for that is going to be 281. If you match up 281 on the reference table, it's 11 protons, 11 electrons. It's got to be ground state. That's ground state. That's ground state. I'm going to highlight my answer. Move on forward. So choice D. Number 2, which of the following is an excited state configuration? Which one of these is excited? So you can match them up with the reference table. A lot of C's. I got a B. Choice B, you have 2 plus 8 is 10, plus 3 is 13. We're analyzing aluminum. 283, it's appearing on the reference table. So that is going to be the ground state. So choice B is ground state. 282 would be on the reference table as well. Choice A, that's ground state. Best answer is going to be choice C. That is not going to appear on the reference table. So I'd add 2 plus 6 is 8, plus 1 more is going to give you 9. Find element number 9. It's F, fluorine. 2,7 is a ground state. 261 would be the excited state configuration. So choice C is the best one. Give one possible example of an excited state configuration for oxygen. Yes, Joseph, thank you. Yes, Kai. Nidal, you can't have more than 2 electrons in the first ring. Kind of open. All right, so it's got to equal 8 total. So if your answer doesn't equal 8, then you're not going. That's not right. Yes, Tristan, thank you. All right, so a lot of answers there. Let's check out a couple. So if someone put 1-7, 1-7 would work out. What happened there is that person took 1 electron for this first ring and added it to the second ring, which is fine. That's what I would do. I'll take 1 from here and add it to the second ring, or even to another ring. That's one answer. Another answer that I saw was, let's see, 251, 5, 6, 7, 8. That would work. 251. 2 in the first ring, 5 in the second, and then 1. So that person just took 1 from the second ring and added it to another ring. That's good. Thank you. 4, 4 would not work because the maximum number of electrons you can have in the first ring is only 2. So you can never have more than 2 electrons in the first ring. You can never have more than 8 on the second ring. So think of that process as well. 2-8 is going to be a totally different element. So 2-8, if you add them both together, 10 electrons. That would be neon if it was 2-8. 2-7. 2-7 is not going to work because you need it to add to 8. They have to add up to 8 electrons. 2-4-1-1. 4, yes, that'd be good. All right, so there's several answers you put there. I'm going to go with those 2. Number 4, question reads, when an atom of the element in the ground state absorbs enough energy, if something absorbs energy, what happens to it? Please put your answer in the chat. Yeah, Tristan. Alex, good. You have an element, you light it. If it absorbs energy, it jumps to an excited state configuration, jumps on up to excited. So that comes from here, jumps on up, absorbs energy. There. And the opposite one, here we go. If the excited electrons lose enough energy, they, please put in the chat. Yes, Joseph. Tristan, good. Alex. Seem good. A, they fall back down and give off energy in the form of light. Light is then produced. That comes from above as well. Dark line spectrum is produced by, how do you get those dark line spectrums? Dark line spectrums. dark line spectrums. Yes. C, they absorb energy and jump to an excited state. Absorbing energy, they jump on up, they're excited. If you absorb energy, light a fire in an element, they're going to jump on up, they're going to be excited. Bright line spectrum is produced by yes, Joseph, Kai, Michael, thank you. Bright line spectrum, check it out above. It's not C. It is A. Bright line spectrum is produced by, that's a huge one. Bright line spectrum is produced by electrons emitting energy and they fall back down to the ground state. There may be a question like that in the benchmark. They love that concept on the Regents every year. So you should definitely know how the bright line spectrum is produced. How is a bright line spectrum produced? They fall back down to a lower energy level and gives off light. When electrons go from ground state to excited, they absorb energy. But when they fall back down, as they fall back down, light is produced. Last question, last thing for the entire unit packet or unit notes. Base your answer to the known bright line spectra produced of the four gases below. Which gases are present in the unknown mixture? So if you're analyzing this question, what I would do is maybe take out a piece of paper or a highlighter if you had a paper in front of you and could analyze it. I lost my pencil, that's why I have to pull this up every time. All right, so it's gonna be tough for me to write on this because my toolbar for Zoom is like stuck right on the top. I can't move it. If you guys know how to move it, I appreciate it. But anyways, let's just check it out. I could manage it somehow. So let's go through this. So mixture A, you have gas A, gas B, gas C, gas D. You have an unknown mixture. In order to be inside this mixture, every line of each of the gases, A, B, C, or D, must be present within the mixture. So let's go through this process. Checking it out now, you have a spectrum, Roy G. Biv. Maybe it's this way, maybe it's the other way. So I'm going to analyze the first line, which is, I'm going to call it red, right there. Then followed above. It's not present in D, not in C, not in A, B, but it is in A. So that's present. Next line in the mixture is here. It looks like it's here. It's nowhere else. So it's just in D. Next line, looks like it's here. And it's not going to be in D, it's not in C, it's not in B, but it looks like a match up to this. These little lines would indicate wavelengths, but there's no measurement on these wavelengths. So there's a certain span of where they would be. This blue one looks like it's going to be here. And then the last three, blue again, mixture, you have this band right here, then it looks like it might be this one. Nothing else above, following on up. The next one, we'll call it blue 2. There's a band there, and it looks like it's there again. And the last one all the way to the right, there's that band. And that's too far off, doesn't match up. So having a piece of paper in front of you would help you out, see if they really match up. All right, so I went through every element, every portion of the mixture. You can see they're all highlighted down there. Gas D has every line indicated, so that has to be in the mixture. Can't be gas C because there's not one thing checked off there, so that's not going to be in there. Gas B is nothing checked off. This has every line checked off, therefore that is in the mixture as well. What's in this mixture is going to be gas A and gas D. So A and D. In order to be in the mixture, in order to identify the element, every band must be present. If this wasn't highlighted, then that's not going to be in the mixture. So you will definitely see a question just like this on the ExoPass, and tomorrow you'll see one on the benchmark. So make sure you know how to identify what's in a mixture or what's not in the mixture. All right, that wraps up unit number 3, the atom. I'm gonna end up with a video on this topic, and then we'll move on from here. Exciting electrons, one of my favorite ones. Enjoy.
Yo, Sparky, you got a flashlight?
Yeah, here it is.
Light, light, it scares away the fright. Soothing incandescence in the middle of the night. No more bed at sunset, much to our delight. You know we all adore it, but what the heck is light? Look at the electrons all happy in their shells, zipping right along, their life is pretty swell. Each one has their own amount of certain energy, and they will stay forever if you let them be.
Just leave it alone.
No. But if you kick an atom squarely in the pants, electrons get excited and will do their special dance. Some absorb the energy and move to higher shells,
Boing.
and leave behind blank places in the spots that they once dwelled. What goes up must then come down, it's not a silly beast. When electrons fall back down, extra energy released. Whatever made them to proceed in their upward flight, when they give off energy, it's in the form of light. The farther that they fall, the more power has the light. The shorter is the wavelength, the waves will be packed tight. The higher is the frequency of wavelengths that will pass. Light is made of photons, which have no charge or mass.
Hey, it doesn't weigh anything.
Light, light, it rises with its might. Phosphorescent stars in the middle of the night. Sealing constellations, much to our delight. You know we all adore it, but what the heck is light?
We love you, light.
Light comes in many flavors, depends on energy.
Chocolate.
Only a slight range of light is light that we can see. From red to blue to violet, mnemonic we can give. It's easy to remember, it is Roy G. Biv.
Howdy, Roy.
Light with lower energy starts with radio.
Hello.
Listen to your music anywhere you go. Radar has more energy, cops use it on their beat. Then comes infrared, which is given off with heat.
Man, that's hot.
Ultraviolet rays can cause sunburns at the lake. X-rays go through all but bone to see if there's a break. Finally, there's gamma rays, but they have so much juice. They go through almost everything if you set them loose.
Don't let them out. I'm going to.
Elemental atoms give off bands of colored light.
Pretty.
It's called the bright light spectrum because the lines are bright.
Duh.
Each elemental spectrum is different from the rest. Identifies what element you have in a test.
Let's see, do we have calcium here or do we have sodium? How do I tell?
Light, light, it rises with its might. Aurora borealis in the middle of the night. Glowing in the northern sky, much to our delight. Now you know the truth. Light, it scares away the fright. Soothing incandescence in the middle of the night. Glowing in the northern sky, much to our delight. Now you know the truth about the wondrous thing called light.
Told you it was like an awesome video. So that is light. A little bit more information about light. Okay, let's go on to the next little portion of class. We're all done with unit number 3. That is due. It has to be turned in by.
Did we turn in the packet yet?
Yeah,
Or did
by Saturday. So if you need to work on some more, you're more than welcome to check it out. I'm not going to check it out till after Saturday. Yes, Jumila. There's different amounts of energies associated with it. That's going to be more of a topic for physics. If you take physics next year, you could learn about how much energy is associated with each jump that's going to be given off. Good question, though. But I'm not going to focus on that at this level. There is, but don't need to worry about that for this one. Our unit 4 is going to be the periodic table. What's going to happen now from the rest of the class is just going to be like the bare basics about what you should know or already know about the periodic table. So I'm going to introduce it. It's going to go quick. Just a little heads up. It is going to go quick. Please click on the link for periodic table. So the periodic table, here we go, unit 4, periodic table basics. Please click on that. And what we're going to do is going to look similar to just show you where we're going for today. This is what period 3 and 4 did. Something like this. So again, if you want to rewatch this, because I'm cruising now from now to the end of the class, you will construct something that's going to look very similar to this. So all this will be done. I know there's not a ton of time left, but we will get all this done by the end of class today. That's our goal. It will go quick. So again, please open up the document Periodic Table Basics. It's in guided notes. And we'll go through a lot of the fundamentals that we already know. Some of the stuff will be newer stuff that you might not know yet, but we will complete this chart, this section of guided notes. All right, so if we were in school, I'd color this, and it'd take a long time to do it. I like the advantage of using the Chromebooks or whatever you're using to fill it in and color it and organize it as well. So we'll take advantage of it. We'll color this in, we'll highlight it. You know a lot of skills to do that. So here we go. We're ready. So what's going to happen, we're going to double click on the periodic table of elements. It's going to bring you to the drawing board. Try not to move this background around too much. If you grab it, you can move it around, but try not to move it around too much. So the first thing is we're going to take a text box. Try your best to stay with me. I'm going to go fast. Take a text box, put it on group 1. So let me hold up for a second. There are 18 groups of the periodic table. Let me zoom on out for a second before I even do that. There are 18 groups of the periodic table. Groups go up and down. So it says it right here, group. There's one group, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 groups. Elements in the same group have the same number of valence electrons. Group 1 has 1 valence electron. Group 2 has 2 valence electrons. You can see that. Don't worry about group 3 to 12. They're a little bit funky. The main groups are 1, 2, 13 through 18. Group 13 has 3 valence electrons. Group 14 has 4. Group 15 has 5 valence electrons all throughout the group. 16 has 6. 17 has 7. 18 has 8 valence electrons. Elements in the same group have the same number of valence electrons. Therefore, they're going to have similar chemical properties. So a lot of times, group 1 bonds with group 17. Why? Because this guy has 1 valence electron. Cl has 7. If you add 7 plus 1, it gives you 8. That makes a stable octet. Group 18, they do not bond. So we'll talk about that stuff. We'll put all that stuff in there. We'll throw the charges of some of these in there as well. But there's 18 groups. Groups go up and down. Periods go from side to side. There's 1 period, 2 periods, 3, 4, 5, 6, 7 periods on the periodic table of elements. We should know elements in the same period have the same number of rings. So every element period 4 has 4 rings. I don't care where you look at it. Every element period 4 has 4 rings. If you're in element period 2, it has 2 rings. We should know that one as well. We should know the 2 liquids, mercury, bromine, 2 liquids. All right, let's put some of this to paper now, or digital. So double click on it. We're going to analyze group 1, putting a text box here around Li all the way down to Fr. Li to Fr. So make a text box. I'm going to change the color of the border. I'm going to make it blue. You can make it whatever color you want. I'm going to change the border weight to make it a little thicker so it pops out. This is called group 1. This is called alkali metals. Once you're done with that, save it and close it, and we'll put some information below. So group 1, something happened over here to mine. All right, so group 1, I'm going to color this the same color I just picked for my text box. I think it was a blue. I fill in with the color, so now I can identify, oh, that color is group 1. If you're colorblind, you can maybe make this a different board or weight. Group 1 is called alkali metals, ALKALI metals. They have one valence electron. They have a charge. Let me check out group 1 over here. They have an ion charge or oxidation number charge, group 1 of +1. So that means they want to lose one valence electron. So that one electron there, that one valence electron, it wants to lose it when it bonds. So when an atom bonds, they want to get to a stable octet, which means to get to 8 valence electrons. In order to get to 8, you got to take 1 plus 7. So this will bond with group number 17. This blue might be a little tough for us to see. And this is the most reactive metal on the periodic table. This group are the most reactive metals. One more thing to add about this, these are solids at STP, standard temperature and pressure. Solids at STP. Group 1, a lot of information about them. A lot of it you know valence electrons. I'm sure you know about the charges. Probably didn't know where they bond with or reactive. You probably could have figured they're metals, so they're solids at STP. Standard temperature and pressure. Let's scroll on down to group 2. I'm going to paint this in. I'm going to paint it. So grab the paint can. Mine's ... paint can. Pick an earth tone color. I'm going with green. So second group, group 2. You can see some properties probably popping out at you now. Hopefully you're looking at the periodic table a little bit different so far. I can tell you one thing, you're definitely looking at this reference table, the periodic table, a lot different than you did maybe 2 months ago or a month ago. Group 2, hopefully you are, if you're doing the work. Group 2 is going to be alkaline earth metals, ALKALINE, earth metals. Alkaline earth metals. In group 2, you can see they have 2 valence electrons. The charge, +2, +2, +2, +2. That means they can easily lose 2 valence electrons. The charge is +2. So if they bond, they could lose 2 electrons pretty easily. So if every atom wants to get to a stable octet means 8. In order for this to get to 8, you got to either gain 6 electrons or lose 2. So if you lose 2, you have 2-8. If you gain 6, you have 2-8-8. So either way, it'd be a stable octet. It's a heck of a lot easier to take 2 electrons off, 1, 2, rather than to gain 1, 2, 3, 4, 5, 6 electrons. So it's going to take the easier path. It's a lot easier to lose 2 rather than to gain 6 electrons. This is going to bond with group number 16 on the periodic table of elements. And this is going to be the second most reactive metals. Second most reactive metals. The first most reactive are group 1, the ones with 1 valence electron. Phase of matter, they're all solids at STP, standard temp and pressure. Once you're done with that, I'm going to go above and highlight my portion of the reference table with that same green. Told you I'll go kind of fast today. Hopefully you're staying with me. Double click on the periodic table, adding a text box around group 2. And we know group 2 now are alkaline earth metals. Alkaline earth metals have 2 valence electrons. If you can't keep up, then you can rewatch maybe the last half hour of class, 20 minutes of class. I'm going to try. I just want to make sure I get this all covered. So I apologize. I will definitely slow things down next week and go at a better rate for you guys. I was planning for the benchmark to be next Monday or Tuesday so I could spend a little more time, but the department said No, but we'll be okay. Benchmark exams, 40 questions. They'll be on from everything from Unit 1 to today's class. Just a little heads up. All right, so we will do a review session tomorrow before you have the benchmark. Group 2 of the periodic table has 2 valence electrons, has a charge of +2. They bond with something that has 6 valence electrons, such as group 16, which has 6 valence electrons, and they're solids at STP. So if you can't really hang with me right now, I'd encourage you to do as much as possible so when you go back to submit it and do it, you don't do as much. Next group is going to be group 3 to group 12. I'm going to take another text box, that T. I'm making a text box from group 3. Scroll on over all the way to group 12. So that big chunk right there. Go to your toolbar above and find a colorful color. So find border color. And I'm going with like a pink here. Because these guys, and I'm going to also thicken out the density or the border weight to 4. These guys are known as the colorful elements. So when I did the demonstration yesterday, these are the ones I excited. They give off the different colors in there. They're called transition metals. These are the metals you're familiar with, like iron, cobalt, nickel, copper, silver, gold, zinc. You know that they're going to be solids. You think of those, they're solids. They typically don't bond with anything else, but they can as alloys. How do you make an alloy? What's an alloy? It's 2 different metals melted together, mixed together as a mixture. Save it and close it. There's my transition metals. They're all solids but one of them. So this one I'm going to color the same color. And I really am sorry if I'm going too fast. I don't like being like this and rushing through things, but I want you to have this. I might have time at the end to review some stuff. So this is called transition metals. Transition metals, group 3 to group 12, that big chunk in the middle. The numbers of valence electrons, if we check that out, number of valence electrons from group 3 to group 12. All right, so number of valence electrons, 2, 2, 1, 2, 2, 2, 1. So a lot of them have 2, a lot of them have 1. Number of valence electrons, they vary. So they vary, but they are positive. They're all positive 1 or positive 2. Which means they all want to lose that 1 electron. It's a heck of a lot easier to lose 2 electrons rather than to gain 6 or 7. So number of valence electrons vary. And they're all positive. The ion charges are, wait a minute, I made a mistake here. Number of valence electrons vary. Not positive, that was the charges. I apologize about that. The ion charges are positives, but they all vary. They're +1, +2, +3, +1, +2, +3. So they're going to vary as well, but these guys are positive, which means they want to lose the electrons. It's easier to lose those 2 electrons or 3 or 1 rather than to gain 6 or 7. And these are known as the colorful elements. So these guys, colorful elements. Why are they colorful elements? I'll show you one in a second. Why are they colorful elements? Because if you look at these bands here, the bands of light in the middle, the transition block, transition elements, they're called a D block. They have a lot of bands there. So if you look at the center versus maybe, I don't know, group 1 or 2, this is a little bit more colorful than the rest of the reference table. There's more bands on transition metals than the other ones. All right, so that's transition metals, group 3 to group 12. Probably not going to have to know much about that besides their colorful elements. Next group is group 17. They're called halogens. Group 17. Group 17, halogens. 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 How many valence electrons do we have for halogens? How many valence electrons do we have in group 17? Yeah, group 17 has 7 valence electrons, 7 valence electrons, 7 valence electrons. The charge, there's several charges on some of these, but the first one listed is the most probable charge, the most likely it's going to happen. So the charge is going to be -1. You know what that -1 means. That -1 means it does the opposite of what it says. I'm not taking an electron away, but I'm really adding one more electron. So if you add one more electron, it's going to give you 8 valence electrons. This one bonds with group number 1. Why? Because group 1 has 1 valence electron. This guy has 7 valence electrons. 1 plus 7 gives you 8. It's a stable octet. Bonds with group number 1. These are the most reactive nonmetals. So these guys bond pretty easily. And one more bullet I'm going to add to the bottom. Cut me off for some reason. All 3 phases of matter. This is the only group with all 3 phases of matter. This group is the only one that has all 3 phases of matter. And I'll identify the 3 phases here. So it's going to be the gases up on top. So gases upstairs, and it's going to be the liquid. And then the ones below are going to be the solids. So kind of just like phases. If you have solids, they're going to go on the bottom. They're going to be tightly packed. Liquids in the middle. Then gases, they could escape towards the top. So if you think of this as like a graduated cylinder, you have like a penny on the bottom. Then you have the liquid. And then you have the gases above. That would help out with that too. I don't know if that helps, but. So the solids, I'm going to actually go with the gases. Gases are going to be F and Cl. The liquid is going to be bromine, my element. You should definitely know mercury and bromine are liquids. And the ones below are going to be solids, which are iodine, At, and UUS. So all 3 phases of matter exist in this group. It's the only group that has all 3 phases of matter. Again, I know I'm going fast. I apologize. May want to rewatch it if can't keep rolling. I apologize. I forgot to put something for group 3 to group 12. Forgot to put the phase of matter. All our solids. I'll put solids at STP. Except there's one element that's not a solid here. Except mercury, which is Hg. So all our solids at STP except for mercury, which we will identify as 2 liquids. Mercury is going to be a liquid. So mercury is the only one in that group from 3 to 12, which is going to be a liquid. 2 liquids, mercury, bromine. Mercury is a liquid, my element's a liquid. Mercury, brown, bromine, liquid. 2 liquids, 35 and 80. 35 and 80. Halogens, I'm going to paint that. And I'm going to paint that a different color. I don't care which color you pick. So find your paint can. One orange. And then I'm going to outline it above as well. So here's group 17. I'm going to outline it with a text box. I'm going to double click it. I'm going to add a text box. There's that group. from F to US. And I'm going to fill it in with the exact same color that I'm going to highlight it with the exact same color that I just picked before. That's halogens. Halogens are group 17. They have 7 valence electrons. Their ion charge is typically -1, which means they typically can gain an electron pretty easily when they bond. So they can take an electron rather than give off 7 a lot easier. You have gases, bromine's a liquid, and then solids are going to be below. They bond with group number 1 very easily. This guy has 1 valence electron. Why do we skip 13? Those guys are just like poor metals. They're not as important for bonding. These are poor metals, and these would be, we'll talk about a whole unit about this guy actually. So they are important, but there's no main group for those. Next group all the way to the right is going to be called inert or noble gases, group 18. I should probably put HE in there as well. I'm going to color this yellow. HE should be in that group too. So HE is in this group. It's a little different though. So this is called inert or noble gases. I'm going to save it and close it. And I'm going to put some information about noble gases next. I colored them yellow. There's group 18. All right, so group 18, they're called noble or inert gases. Noble or inert gases. Might as well color it in the same color I just picked there, so I don't forget that. It's yellow. This guy has 8 valence electrons. You can see that there. 8 valence electrons. 8 electrons in the outer shell. So 8 valence electrons. These guys are completely happy. They're stable. They don't want anybody else to bond with. This is like your great uncle who's single, and he's okay being single. Or your great aunt who's single. That person that's single life, they're okay being single. That's fine. So your great whatever, that's single. That person that's single life, they're happy. They're fine being by themselves. They have 8 valence electrons. They don't want anybody to mess with them. They're living their life on their own. They're happy. They're marching at their own drum. They have a charge which is equal to 0, which means now that they're not going to gain or lose any valence electrons. They're stable octet. Argon, 0. Not going to lose or gain any electrons. It's stable. This guy is stable. It could be +2, but it's going to be really stressed to get there. So this group has a charge of 0, which means typical charge of 0, which means no one's going to bond with them. It's going to be really tough to bond with these guys. Bonds with none. Doesn't bond with anything. And they do not react. Do not react. Phase of matter, gases at STP. Noble or inert gases, gases at STP. And we will definitely go through all this information again. This is a bare basics that you should, maybe some of this information you know, at least be aware of. So noble or inert gases, group 18 of the periodic table. You're saying, hey, Mr. Brown, what's going on? I thought you said they have 8 valence electrons. But helium doesn't have 8 valence electrons. Then you say, hold up. What would you do? Oh, never mind. Helium doesn't have 8 valence electrons, but if we drew helium, my toolbar is gone. I told you that, so I have to do this every time. It's weird. There, and then it pops up. So helium doesn't have 8 valence electrons. So if I draw helium atom, nucleus, and then around the nucleus, you're going to have one shell with 2 valence electrons around it. question for you is, why is that stable? Why is helium stable? Why is that considered a stable octet? Why is it in this group with all the stable octets? What's the maximum number of electrons you can have on the first ring? 2. So why is it stable? Because the first shell is completely filled. So stable really means is if the shell's filled with a stable octet. That first ring could have a maximum of 2 electrons, so that's why it's going to be stable. Yes, you're right with that one too. All right, moving on forward. So that's the noble or inert gases. Lanthanides and actinides, really super simple. That's all the way in the bottom. Lanthanides and actinides are going to be, lanthanides are from period number 6. They should be in period 6. And these are going to be the radioactive or man-made elements. The reagents, the course, we really don't explore too many of these elements. We'll explore a couple of them, but not too many of them throughout the year. Period number 7, they're not very reactive. Some could be, but we'll get to that later. Period number 7 is going to be radioactive or man-made elements. I'm going to color these in as well. I'm going to take a paint can, coloring the first one red, coloring the second one purple. Now I can highlight my lanthanides and actinides. 8 minutes left. We got this. All right, so double click the image. Lanthanides is period number 6. So I'm going to fill this in with a text box. This one I made red. And you don't have to really memorize where the lanthanides are, because if you look at this little arrow, this should be actually inserted on period number 6. So this should be inserted up there. That should be inserted right there. To memorize lanthanides and actinides, which again, I never really seen them ask a question on the reagents. I can't recall when they said, what's the name of this group on the reagents? But in the event they ever do, LA is actually lanthanides. This is a lanthanide series. That should be inserted at that portion right here. So lanthanides should be inserted here. Why don't we do that in the reagents? It's just or the reference table. It's just because if we did do that, then these elements would be so super small. So that should be inserted there. If we threw that up there, then you're analyzing a really long periodic table and it'd be really small. The one below is called the actinides. I think I colored this purple, so I'll do purple here. And this should be inserted in between the periodic table as well. So this portion right here, you don't do all these little lines, just showing you where they really come from. Actinides, AC, you can see that there too. They should be inserted in that portion as well. So there's AC, actinides. That could help identify which elements or the name of the group it is. Lanthanides, actinides, both man-made elements, radioactive as well. The last major group of the periodic table is just one simple element by itself. I'm making a text box. It's going to be hydrogen. Hydrogen is in a group all by itself. It's a lonely element. I'm coloring it teal, and I'm going to bold it as well. This is the most reactive element in the periodic table of elements. It has 1 valence electron. It is a non-metal. That's why it's not attached to group number 1. These are alkali metals. This is a non-metal. Most reactive element in the periodic table has 1 valence electron, has +1 or -1 charge, depending if it bonds with a metal or a non-metal. So let's fill that one in. Hydrogen, I colored it teal. And valence electrons, it's 1. Ion charge could be +1 or -1. You'll know that inside and out by the end of the year. +1 or -1. It bonds with many elements. Could bond with metals, could bond with group 1, could bond with group 2. Bonds with a ton of elements here. Most reactive element. It's a non-metal in a non-metal in a group of its own. It is a gas. Gas at STP, standard temperature pressure. But I do need to put more stuff on here. So it's a gas at STP. Okay, I only have 4 more minutes of class left, so I'm really going to turn it up now. So again, suggest watching the last 4 minutes of class. So here we go. Last thing I'm going to do is going to put the 2 liquids on here. My 2 liquids are mercury and bromine. So mercury, I'm just going to fill that in with a blue color. It's a liquid. And the other liquid's going to be bromine, liquid. Fill it in with a paint can. Okay. We also have metals and nonmetals location. My text box, I'm going to fill this in with a black color to indicate metals are going to be to the left. And I'm going to put some text in there as well. So in this, these are going to be my metals. Color it white. So to the left are metals. To the left are what? That staircase. Metals are to the left. Left of the staircase. So right where that ends is basically where my metals are going to be starting. So metals to the left of that staircase. You see that staircase right there? That's called metalloids. So I'm going to copy this image, Control-C, paste it on in here. And to the right of that, I'm going to put nonmetals because these guys are going to be my nonmetals. I'm going to shift my arrows so it goes the opposite direction. So everything to the right are going to be nonmetals. That staircase right there is called metalloids. So that staircase are called metalloids. And they have properties that are similar to metals and nonmetals, depending on their temperature and their pressure. So metalloids are going to be on that staircase right there. Everything to the left is going to be a metal. Everything to the right is going to be a nonmetal, besides hydrogen, which is a nonmetal. So that's really the dividing point between the metals to the left, nonmetals to the right. I think of oxygen, chlorine, nitrogen as nonmetals. Hopefully think of metals as like silver, gold, aluminum. Everything to the left, they're going to be metals. Okay, last 2 things I have to do is a chart here on the bottom. So again, please rewatch this. The trends, atomic radius is the size of the atom. So as you add more rings, as you go down a group, the size gets bigger. As you go from right to left, the size gets bigger. Francium is going to be the greatest atomic radius. So as the trend is, as you go from right to left on a period and down a group, this atomic radius increases. So the trend for that would be my arrows. So again, find your arrows. I know you can't do this as quick as I can. Maybe you could, probably faster. But anyways, as you go down a group, the size increases, atomic radius, how big it is. The other trend is going to be as you go across a period from right to left, the size increases as well. So in this situation, the greatest atomic radius is going to be this guy. The biggest size is going to be FR. The biggest atom is going to be FR. The smallest would be up in this corner, the opposite direction. I'm going to save that one. That's atomic radius. It's the size of the atom. The last one's electronegativity and ionization energy. It's the same trend. And this trend is going to be as you go across a group, as you move across a group, across a period from left to right, and up a group, the trends increase. And we just put these last trends in here and pretty close to done. Again, please rewatch these videos. Watch the second portion of the video. The trend's going to be from right to left. It's going to increase for electronegativity. That means the ability to take in electrons. So which one's going to take in electrons easiest is going to be F. Which one's going to take them in the easiest? It's still going to be F in this situation. Let me just bold these on up. Bold. Bold. Again, the greatest electronegativity is F. Greatest electronegativity, F. Okay, saving and closing it, and there's just one little. So this is the exact same trend as the one above. Last thing for today, metals are located to the left of the periodic table. They're malleable, they're ductile, they're drawn into wire, they're good conductors for heat and electricity. And they reflect light. Non-metals are going to be located. Non-metals are located to the right. What's going on here? Great, we're a minute over. If you have to go, feel free to rewatch this. They're located to the right of the periodic table. They're not malleable. They're called brittle. I don't know what's going on here. They're not ductile. They're not good conductors of heat and electricity. They do not reflect light. So again, tomorrow I will do a review session before the benchmark. We'll go through a couple more things here. We'll review some stuff. No more new material, but this stuff, I don't know why it won't work out. They're not malleable, they're brittle, and they're not good conductors of heat and electricity. So tomorrow you're having the benchmark. It's going to be on everything from Unit 1 to some of the stuff that may be on here as well. I know I cruised through it, so you may want to watch the video again, at least the second half of the class. We will review again. Review Unit 1, 2, 3, 4. There will not be any questions on heats, Q equals MC delta H, that stuff. There's not going to be any questions on heating curves or cooling curves. There's no vapor pressure questions. There's no ideal gas questions either. There's no pressure questions. So some stuff from Unit 2 could be snipped away. I'll be here if you have questions. Have a great day. Make a decision. Study on up. I'm sorry I rushed through class today, but I want to make sure you have the tools for success for tomorrow. Have a great day. Decisions. Be safe. Bye, Nadine. Have a good Bye, Kai.
Thank you. Have a good day.
Have a good day.
Hey, you too. We'll see you later. See you
Mr.
later,
Brown?
alligator. Yes, Jordan.
Since like the marking period is ending soon, like what are we supposed to have in before like it ends? Because I don't know when it ends.
Benchmark. We have everything up till this week. Everything from this week, at the end of this week, that's the end of the marking period for me. Some teachers might stop their cutoff day at a different time, but mine's at the end of this week. So every exit pass, all the tests, the last 2 tests, this benchmark will be in there. If you want to do the extra credit, you could do that, but obviously the notes have to be submitted too. This one and last unit as well have to be submitted. Those are going to quarter 1 as well.
All right, so everything is due by Saturday, basically.
Yeah, Saturday's my cutoff
Okay.
for that. Yep.
All right. Have a nice day.
You too.
Thank
Sorry
you.
to rush through this stuff. We'll see you later.
Fine.
Joey G. See ya.